Hello everyone. Let's begin with the second part of this numerical of tau to tau connection. So in last video we choose a channel section that is ISMC 300 and we calculate design compressive strength and found out that it was safe. Well, in last video I just forgot to mention about this value, that is 351.2 Newton per meter, but it's just nothing. It's a simple calculation, that is conversion. If you see value ISMC 300, that is 35.8. Here it is given, that is weight per meter, so it is 35.8. So if you multiply this 35.8 into 9.81, that is if you convert this weight per meter into Newton per meter, that is if you convert this 35.8 into Newton per meter, then we will get this value 351.2 Newton per meter. So we can multiply this value with 9.81, you can get exactly this value. Okay, so let's begin with our further procedure. So before beginning continuing our numerical, I would like to say please like this video and subscribe to my channel, so it will encourage me more and more to upload more number of videos. So let's begin with next part of our numerical, that is spacing. Okay, spacing of channel. So spacing, you can see my last numerical, that is numerical related to back-to-back connection. The spacing is distance between the edge of a first channel to the edge of second channel is known as a S. Similarly, even in this case, that is tau to tau connection, the spacing is distance between the edge of first channel to the distance between edge of second channel. So total it is written as S. So you have to notice one more thing, that is the center of gravity of this channel, that is CYY. You can see here CYY. So CYY is the distance from the edge of this channel to certain point. So I'll draw you from here. See, from this point to this point we can write like CYY. It is the center of gravity. So this, we can see this particular line, this is the y-axis for this particular channel. So if we'll consider for whole system, this is y-axis and this is our x-axis or z-axis, whatever we can say. Fine. So for better connection between two channel, there is one flowing criteria for greater stability of this whole system. So whenever we are going to connect any two number of channel, okay, so it must fulfill this criteria, so you will get more stability in a whole system. That is, moment of inertia about x-axis must be more equal to moment of inertia about y-axis. Well, you can see in this case, if you see this particular channel, it is symmetry about x-axis, but it is not symmetry about y-axis. Fine. So it is symmetry, though it is symmetry about x-axis. We don't have to do anything for this side. Instead, we have to multiply by 2 because there are two number of channel. Fine. For this case, we have to multiply by 2. Also, this is this channel is unsymmetric about y-axis. So whenever the system is unsymmetric about any axis, there is one certain formula, that is yi plus area times the distance between CG of this particular section to distance between the CG of whole section. So it will be like from this point to this point. So we know the total distance is S, right? So the half of the distance will be S by 2. Fine. And the distance from this line to this line, it will be S by 2 minus CYY. That's it. So S by 2 minus CYY. Since this section is unsymmetric about y-axis. So you must have seen this formula in terms of like I y plus a x bar whole square. So it's just in this format of this. Okay. So I just explain you about this. In back-to-back channel, if I talk about back-to-back channel, the distance is this is S. So it will be like half of the distance will be s by 2, and then half of the distance will be s by 2. The distance from this channel to axis of this particular channel will be like cyy. So total distance will be my s by 2 plus cyy. So in back-to-back connection, you can see this formula instead of this one. So in back-to-back it will be plus, in tau it will be minus. That's why I have already explained you. So let's go through direct value. So we know that we know the ix value, we know iy value, we know area value, we know cyy value. So we have to find out s value. So you can see here I just wrote this value from our given data, that is what we have obtained from our code book. So 2 times 6, 362.6 in 10 power 4. Ix, Iy is 310.8 10 power 4. Similarly, we don't know s. We know the area, that is 4564. Actually, we have already multiplied by 2. That's why you have to take just area of one channel. And then again, CY is 23.6 mm. So finally, we get spacing of channel, that is 277.5, which is approximately 278 mm. So first job we choose our ISFC section. The second job we choose our spacing of the channel. Now the third one we'll go for lacing bar. Okay, finally we go for lacing bar because we choose the channel, we choose the spacing. Now we'll go for lacing bar. So in lacing bar, the first we have to decide the spacing of this lacing bar. The spacing is nothing, distance from the end of first channel to the end of the second channel, that is second member. It's not a channel, it's just a member, one plate. Okay, so distance from this end of lacing bar to the distance from this end of that is next end of lacing bar. Okay, so this is known as a You can see in diagram, it is known as a Fine. So in lacing bar, the first most important thing, you have to decide inclination of lacing bar. So inclination can be done from 40 degree to 70 degree. So I normally prefer theta as 45 degree. So you can see here, I normally prefer it as a 45 degree. Okay. So you can see this lacing bar is bolted at this point and it is bolted at this point. Alright, so you can see in a figure, this is suppose this is the bolted point and this is a bolting point in this channel, and similarly this is a bolting point in the second channel. So the distance from bolting point to edge of this channel, that is edge of any channel, is known as a G, which is also known as a gauge distance. Fine. So now we have to find out this value, A1. So to find out this value, we can go through some simple trigonometric numerical. Fine. So the first job we have to find out distance from this bolt to distance from this bolt. So you can see the total distance will be our S. Okay, total distance will be our S. So distance from the edge to bolt distance is known as a G. So distance from edge to bolt distance will be our G. So the total distance from this bolt to this bolt, it will be like S minus G minus G. Fine. So my distance will be like, this distance will be 278 minus 50 minus 50. Fine. So now we have to find out this value, that is B value. So let's consider it as a triangle. Let's consider it as a triangle. Suppose this is your triangle. You know the value like 278 minus 50 minus 50. You know this value. You know this angle, that is 45 degree. So if you are going to calculate the distance from here to here, suppose this is A1. So let's take this distance as a B for some time. So tan theta is equal to, that is P by B. This is our P, this is our H. So tan 45 degree will be like 278 minus 50 by B. We don't know the B value. So B will be like 278 minus 50 got 45 degree. So if we'll multiply this b with 2, that is, if in twice of b will be our a1. So we can write a1 as like 2 times 278 minus 50 minus 50 got 45 degree. Okay, so why I am getting a1? Because we have certain condition which I am going to explain you further. So for the first job we have to find out value of a1. So you got the value of a1. Now so if you calculate value of a1, I'll get around 256. That is 356 mm. Okay, so I'll get value around 356 mm. Now we'll go for further condition. There is two condition, that is there are two criteria which must compulsory we have to do, or we have to calculate that criteria. So two criteria must be fulfilled. The first one is a1 by ry must be less than 50, and the next one a1 by ry must be lesser than 0.7 times kl by re. So any one of them, whenever any one of them will meet the criteria, you can go for further procedure, but you have to check this both of the condition. Fine. So let's go. We know the value of a1, that is 356. We know the value of ry, that is 26.1. So it is 13.6398, which must be less than 50. I told you it's okay. The next one, or a1, we know the value of a1, that is 13.6. we already got this value, 13.63 must be lesser than 0.7 times 88.90. we know the value of kl by re is 88.90. so you will get around 62.23. so it's okay. Now we can go for further procedure. So sorry, this is just a constant. Okay, so let's go through now the forces, how it will react, or how it will we can observe the forces, how it will act on this member, on this system. Okay, so let me find out. The first is maximum shear. So maximum shear is 2.5% of total load. So 2.5 of total load will give me 1080 into 10 power 3 will give me 27000 Newton. Similarly, this is noted as like, so therefore Vt will be my 27000 Newton. Now the second one is transverse shear in each panel. So transverse shear will be like Vt by n. We have two number of channels, so 27000 divided by 2 will give me 13500 Newton. Now we have to find out the compressive force in lacing bar. Compressive force in lacing bar. So you can observe here. Okay, you can observe here in this diagram. See, this is my transverse shear, that is Vt by n, what I just calculated here, Vt by n. This is my Vt by n. So if this force will act in this direction, we know this is a 45 degree. So first, sometime this let's go through trigonometric calculation. This is our P, this is our B, and this is our H. So sin theta will be P by H. So I need the force in this direction. So H will be like P by sin theta, that is P cosec theta. So direction, the total forces, that is compressive forces in this member will be Vt by n cosec theta. That's why compressive force in lacing bar we can write it as a Vt by n cosec theta. So if you calculate this value, that is Vt by n, we already got this value, into cosec 45 degree, you will get 19.09 kilonewton. Okay, so you have to observe here. Actually we just calculated all the forces. Now you have to observe here in this diagram. this is really so much this is really important for you to for the further calculation, that is connection system, how the number of bolt, what is the number of bolt and all. That's why you can see this is bt by n is our transverse shear in this direction, right? So bt by n is cosec theta in this direction, this is compressive force. Okay, so if you want to calculate the forces in this direction, okay, in this direction, so if you resolve these forces, you will get bt by n cos theta. So at this point there is the forces act in this particular bolt will be bt by n cot theta from this member as well as from this member. So bt by n cot theta, bt by n cot theta to this bolt. So I'll explain you later about that. Let's go for further step. So we calculated spacing of lacing flat. Now we have to design this lacing flat, this particular section. Okay, so it is like a plate, it is like a plate like this, it is like a plate. Okay, so it is like a plate. Now you have to calculate width, its thickness, and we know the length. Okay, because we can calculate this length without this simple trigonometric calculation, because we know the distance from this bolt to this bolt. So the distance is like let's write here. Okay, it will be so much clumsy here. So s minus gauge distance 50 minus gauge distance 50, this is our distance. So if we'll convert this distance into like inclined distance, total length of this flat, we have to multiply with cosec 45 degree. It is a simple trigonometric calculation. I'll explain you later. Okay, so the first job we have to find this width lacing flats. So let us assume 16 mm dia bolt. Okay, so for a whole numerical I just assume 16 mm dia bolt. So width of the flat will be 3 times of 16, that is 48, so around 50 mm. So I got the width of the lacing flat. Now I have to calculate thickness of the lacing flat. So minimum thickness of lacing flat is equal to, there is one formula, 1 by 40, which is given by your code book only. 1 by 40 distance from this bolt to this bolt. So what I mean is, suppose you have got your channel system. So if this is your lacing flat, so distance from here to here, so we know that this distance is s minus 50 minus 50. Okay, so if you convert this distance in this simple, you can go for simple trigonometric calculation, that is like this is your p, this is your 45 degree, and this is your h, and you know this value, that is 278 minus 50 minus 50. So if you can find this h, so it will be like 278 minus 50 minus 50 cosec of 45 degree. So it is around 6.29, approximately 8 mm. So minimum thickness for this flat is 8 mm. Okay, so we calculate, we know the length of this flat, we know the length of this flat, we know the width of this flat, we know the thickness of this flat, So now we have to check whether this lacing bar is stable or not, or what the dimension we choose is correct or not. So for that calculation, we have to calculate R minimum, that is like you can see direct formula T by under root 12. So this formula is obtained from this condition, Bt by B into T. You know this is I, you know this is A. Okay, because we know R is under root I by A. So I is BTQ by 12 and area is B into T. I am talking about lacing flat. See, this is my width B, this is my thickness T. So BTQ by 12 and B into T is my area. So I'll directly, you can see in book that is t under root 12. So it can be converted in similar form like this. Okay, so the value will be like t is my thickness is my 8 under root 12 is equal to 2.309 mm. So we know the value of r. Fine. So we got value of r. Now we have to find the value of L by r. So L is 178 cosec 45 degree by 2.309. I have already told you about length of the lacing plate. Fine. The length of the lacing plate. Length is 278 minus 50 minus 50 cosec 45 degree. This is 178. Okay. So 178 cosec 45 degree will be length of this flat. So I'll get value around 109, which must be less than 145. So let us provide 50 ISF 8 mm flat. Okay. Now let's check. Let's go for a further calculation. So let's check whether this section is okay or not. For L by R, I am just going to check whether this lacing bar is able to withstand load or not. So for L by R, our L by R is 109.00, and we know that Fy is 250 megapascal. We have to find FCD. Okay, so FCD. So you can see we have to find FCD. So before that FCD, you have to see this is our rectangular section. Okay, for rectangular section, buckling class C, you can see here, this is our rectangular section. So for rectangular section, it is buckling class C because we took lacing plate as a rectangular section. So buckling class C. So we have to find out like FCD value. So FCD value we can get from table 9C, design compressive stress FCD for column buckling class C. So our value lies, that is our value is 109. L by R. L by R is 109. So L by R is 109. That is between 100 and 110. That is 109. Similarly, I told you we have to go for Fy, that is 250. So choose 100. For 100 value it is 107. Okay, for 100 it is 107, and for 110 it is 94.6. It is 94.6. Now we have to find out this x value. So after calculating, I got the value of x through interpolation method, 95.84 Newton per mm square. So my FCD is equal to 95.8 Newton per mm square. So now my total design load will be FCD into area. So FCD into area, if I multiply FCD into area, I'll get around 95.84 into 50 into 8 is my cross sectional area into 10 power minus 3. So I'll get 38.33 kilonewton, which is greater than 19.09 kilonewton. So this is our compressive force in lacing bar we calculated, and this is 38.33 is its strength. So it can easily calculate this value. So 38.33, this is the design strength of a lacing plate, which is greater than this 19.09, which we already calculated already. We already calculated. I just told you. So we have already calculated like compressive force in lacing bar. This is 19.09 kilonewton. So we can see here it's 30.833. It is obviously greater than this 19.09. So it can easily withstand this load. Fine. So let's go for further calculation, which is a final step and final procedure. That is a connection system. So for connection system, I already explained you that I assume 16 mm diameter of bolt. So it's just a lacing bar placing, you can see in this figure. Okay, there is two type of system of placing this lacing bar. The lacing bar is placed one after another, that is one, there is lacing bar and another lacing bar is there, that is overlap, and the next another lacing bar is there, it is again overlap. The next system is there is one lacing bar and there is one more lacing bar, there is one more lacing bar. So in this case there is independent lacing bar is bolted. In this case there is lacing bar which is overlapped is bolted. So now we have to find the strength of a bolt. So there are two types of strength of bolt, what is shearing and there is bearing. So strength of bolt in shearing, that is it will be double shear, because suppose this is your channel, okay, this is your one lacing bar, there will be one another lacing bar, it is overlap. So there is three channel, 1 2 3, so there will be two interface. Okay, that's why 2 times A and B times FUB by under root 3 into gamma MB. So 2 times A and B value is nothing but just 0.78 into pi by 4 d square, diameter is 16 square, so you have to take this value A and B. So 157 into FUB, ultimate bolt strength is 400 into 10 power minus 3, I am converting into kilonewton. So we can get this value 58.01 kilonewton. Similarly, strength of bolt in bearing 2.5 kb d t fu under root gamma mb. All this formula you can get in code book. So 2.5 kb, I just assume value kb because this numerical is already too long, so we can go for calculation of kb. So you can directly assume value of kb is as a 1. Your diameter is 16 mm. Thickness of plate is 8 mm. We choose the lacing bar of 8 mm thickness, and Fe is 410 by gamma mb 1.25 into 10 power minus 3. I'm just converting into kilonewton, 104.96 kilonewton. So see which one is lesser, this value and this value, which one you have to compare both of these value. So obviously strength of bolt in double shear, this value is lesser than this value, so we'll add up this value. Okay, 58.01 kilonewton to find out the number of bolt. So if we'll calculate strength of bolt in single shear in this case, then it is same as it is like how we calculate strength of bolt in double shear. Only there won't be this value 2, because there is one channel and one plate, there is only one interface, so no need to multiply with 2. So A and B into FUB under root 3 gamma MB. If you calculate this value, you will get 29 kilonewton. Just divide this value with 2, you will get this value. So in this case number of bolt, and I calculate in this case number of bolt. So if you calculate in this case number of bolt, so we have to find out force in lacing bar. So force in lacing bar, we can calculate force in lacing. So you can see in this figure, I have already told you that this is my BT by n, this is BT by n cos sec theta, and the direction in this direction it will be like BT by n cot theta from this lacing bar and from this lacing bar. There is two lacing bar. Fine. So BT by n cot theta. So force on bolt from lacing flat will be 2 times BT by n cot theta. 2 times BT by n cot theta will give me like 27.0 kilonewton. That is 2 times 13.5 into cot 45 degree. That is 27.0 kilonewton. So number of bolt required is equal to the force which is acting in this bar divided by strength of bolt. So my strength of bolt in this double shear is like 58.0901, that is 58. So 27.0 divided by 58, it will be like 0.456. So at least we have to take one number of bolt. So that's why there will be one number of bolt. Okay. So if you will calculate in a single shear, so you have already calculated strength of bolt in single shear, that is 29 kilonewton, and you have already calculated force in compressive force in lacing bar, that is 19.09 kilonewton. Last time we did, that's compressive force in lacing bar 9.09 kilonewton. So the force in this lacing bar divided by strength of bolt will give you number of bolt. So even in this case we will get one number of bolt, 9.09 divided by 29.01, that is 0.658, which is approximately 1. At least you have to take 1, because there won't be bolt in a fraction. So 1, 2 or 3 or 4, whatever. So we will get value at 1. Now total this is the connection system. Okay. I know this numerical is too long, so there is one more step left, that is final step, tie plate. Okay, so this numerical will help you, this portion will help you to solve numerical in baton system too. Because there is a lessing part and baton part in this compression member, so it will help to solve numerical in baton part too. So it has just got a formula. So we are designing n typelet. It is a typelet because there is one channel and there is one more channel, because we are connecting two of the channel. So at end we have to connect with plate. We can't go directly with lacing bar. Okay, so we have to connect with a plate at first. Okay, so the effective depth of plate, is given by one formula, that is s minus 2y. So effective depth is distance from center of this pole to distance from center of this pole. It is a effective depth. Okay, s minus 2 cyy. And we know that this one is a edge distance. Okay, so edge distance, diameter of a hole, we know the diameter of bolt is 16, so therefore diameter of hole will be plus 2, that is 16.2, 16 plus 2, it will be 18 mm. So minimum edge distance, it will be like 1.5 times 18 mm, that is 27 mm. Approximately we will take 30 mm. So the total distance, it will be s minus 2 cyy plus 30 plus 30. That's the total overall depth will be your 230.8 plus 30, that is 290.8, approximately 300 mm. So length of the lacing flat, length of this type plate, length of this end baton or a type plate. So length will be like total spacing. What is your spacing? See, from this edge to this edge, it is like 278. So you can take it as a 278 directly. Okay, so for thickness of a flat, 1 by 50 minus 278 minus 2 times gauge distance, that is 278 is your length of the plate. Okay, this is your length of the plate minus 2 times your gauge distance. So you will get around 3.56 mm, that is around 6 mm. So we got a type plate that is 278 into 300 into 6 mm. Okay, so the numerical we solved is a single lacing system. Sometimes they might ask you a double lacing system. In double lacing system, please don't forget, actually we calculate about single lacing flats, right? So we calculate minimum thickness of lacing flat. So in case of double lacing system, the minimum thickness of lacing flat will be 1 by 60 times your 278 minus 50 cosec 45 degree. This is the difference between a single lacing system and double lacing system. So they might ask you sometimes a double lacing system. So instead of 1 by 40, it will be 1 by 60. Okay, so this is all the numerical. So if you want more numerical, more videos, please like my videos and comment in the section so that I could upload more number of videos. Thank you.